our invited speaker, Dr. Hannes Hubel, Senior Scientist at the Austrian Institute of Technology. He is the thematic coordinator and in charge of all quantum technology activities at the AIT. As a senior scientist, he is also responsible for the experimental quantum key distribution developments of the group. He is very much involved in the European quantum technology flagship effort as coordinator of several large projects in the quantum communication pillar, and besides his research work, he is also consulting the European Commission on the deployment plans for its large quantum communication network, the EuroQCI. Dr. Hannes, the floor is yours. Thank you for being here with us.
Okay, thank you very much, Elias. Yeah, it's really a pleasure and honor standing in front of you giving this keynote speech. Before I start, I would like to thank the organizers, Ministry of Digital Governance, the Fourth Institute of hosting us. Really wonderful location, but really special thanks, I think, to Elias and his team at GRNet and the University of Athens for really putting this effort in to have those training events. And I think we already heard, I think it's really important, those training events, because since it's such a multidisciplinary field, quantum communication or even QKD, you basically need quantum physicists, optical engineers, electronic engineers, software developers, network engineers. That is something really hard to basically learn at university. So I think it's really good to have those training events where basically all those experts come together and you can learn from them. Good. For my keynote speech, it's always a bit tricky what you put in. So I will try to basically give a very broad overview of the field. Quantum communication, I will touch a bit of other quantum technologies as well. Also try to basically put it a bit into an historic perspective. And that will mean I will not have a lot of time to go into details. I will leave a lot of gaps and holes behind me. But I've been looking at the list of the speakers after me, and they're really excellent in their fields. So they will hopefully fill very competently all the missing gaps that I have. Good. Training in Crete. So when I first got the email from Elias, it somehow rang a bell. And we are here now in 2024 in beautiful Heraklion. But nearly 20 years ago, I was already on the island, also on a training event. It was organized in 2005, a NATO advanced study course in Chanias on the western side of the island. And the topic there was really interesting. It was on quantum information processing at that time it was called. It was not yet quantum technologies. And the title was really From Theory to Experiment. And it was really at that time that the first kind of wave of experiment has started to develop. The first real results came in. And so they had basically this study course there to really, again, educate a young generation of what is actually possible. What can you actually do in the lab? At that time, it was a lot of in the lab still, but you could finally, all those nice ideas, quantum computers, which started with Feynman, quantum money ideas, even BB84, QKD protocols, you can finally really implement them in the lab and do real experiments with them. So it's really exciting time. And so was the early 2000s, where people really started to go outside of the lab with their quantum experiments. So in 2002, for example, there was a very famous QKD experiment along the Lake Geneva in Switzerland. So at that time, it was already quite long distance, so nearly 70 kilometers between different cities along the lake. They already went free space as well. So that was another experiment done in the German Alps, where they basically put a transmitter and receiver station for QKD on top of the mountains, and they had a couple of kilometer distance and transmission of QKD keys. And there were also real use cases, or nearly real use cases. So that was in 2004. There was a proof of concept experiment in Vienna, where basically for the first time, two buildings were connected through an optical fiber that went in a sewage system in Vienna. And it was an entanglement experiment, QKD, and it was really used to secure a bank transaction. So even at that time, people have already tried, okay, it's nice to have basically those proof of concepts to basically exchange the keys, but what can you actually do with the keys? And that was, the first bank transaction secured by QKD. So the reason is why those people actually went out in the first place of the lab is really to test the limits of quantum theory. So quantum entanglement, I'm not sure if you're all familiar with it, but it basically is this correlation between two or more quantum particles that whenever you measure, the outcomes are the same. That's a very simplified version of it, but it can be very far separated, and you measure the polarization of one, the other one has exactly the same, and you can basically keep repeating that. And Einstein called it a spooky action at a distance because he was not... okay, sorry, something popped up on my screen here, but I think it's okay. Because he was not happy with this concept, because it seemed to defy reality. But as we know now, it doesn't actually. And people basically wanted to know, okay, they could do that in the lab, but they wanted to basically show, okay, what if we really go to larger and larger distances? Does that actually really hold, or is there kind of a limit to quantum mechanics? So they really started to go out of the lab to do those experiments. So that was one done in Innsbruck, where they had basically entanglement source in the middle, and they went to distribute those photons 200 meters left and right, did the measurements, and still showed or demonstrated, okay, entanglement is alive. And then, of course, you can also do quantum key distribution with entanglement. There was another experiment based on the same setup. So they had a picture. They basically generated Alice and Bob's keys using quantum key distribution, encrypted it, and decrypted it. And if you look very closely on the picture on the bottom right, that's actually the Venus of Willendorf, a very famous statue from the Neolithic times. You see that some of the pixels are actually not quite correct, and that's because at that time nobody cared about post-processing, so there's no error correction done on the picture. So there was a couple of errors, which you basically always have in QKD, and if you don't correct them, of course, you get some distortion in your final decrypted data. And for those experiments, theories at that time, or in the 1990s, we just got the Nobel Prize awards 2 years ago to Alain Aspect, John Clauser, and Anton Zeilinger for those pioneering experiments using entanglement. So why I wanted to show you all this is really to basically don't underestimate the progress of technology, because since then a lot has happened. And if you think nowadays, you basically have those QKD systems, even entangled ones, in a nice 19-inch box. You can basically just take it out of your box if you get them shipped to you, put them into a 19-inch rack, install it, and everything works very smoothly. And that's only, as I said, 20 years ago or later, since those first experiments were actually done outside of the lab. So I think there's a tremendous progress. And I would say our whole world is nearly depending now on quantum mechanics, or the insights that quantum mechanics gave us, because I'm sure that I think nearly all of you will have one of these devices in their pocket. But it really relies, our modern ICT infrastructure really relies on one hand on computing power. So that's basically the invention of microprocessor, so understanding semiconductor solid-state physics. And the second one is connectivity, and that's done nowadays mainly by optical communication, which of course is based on the invention of the laser, which again relies heavily on understanding the interaction between light and matter, which comes from quantum physics. And this can be, those developments can be broadly summarized as the first quantum revolution, which happened at the beginning, mid of the last century. And now we come really to the second quantum revolution. So you might hear this term as well sometimes, and I just want to briefly tell you what it is about. So this first quantum revolution, it was, as I said, solid-state physics, lasers. This is describing really the interaction of light, of matter, but in a many particle system, many body system, if you want to have. What we really do in the second quantum revolution, we really take individual quantum systems, So we don't speaking about light interacting with a cloud of gas molecules, but we're really looking really into individual photons or individual atoms in this gas cloud, and try to basically see how the interaction works like that. And you have really a whole variety of quantum systems there at your disposal. So you can have photons, electrons, atoms, ions, defects in diamonds, in other materials. And those individual quantum systems, you could really think now, okay, they basically carry my information. And given that, since they are basically quantum systems, they behave slightly different to classical systems. And this gives you really then this advantage in the quantum technologies like quantum computing, quantum sensing, or quantum communication as we have. And the main differences are you can basically put those quantum systems in superpositions. Yeah? So you have, for example, a photon, which has polarization horizontal, vertical. You could also make a superposition 45 degree. Or an atom can be in an excited state or in the ground state, but it can also be in both states at the same time, according to quantum mechanics. And that basically gives you a big advantage in quantum computing. You also have this non-cloning theorem, which is especially important for quantum communication, which means that if you give you unknown quantum state, so I give you a photon, which I have prepared in a certain polarization, I don't tell you which one, there's no measurement you can do to exactly find out what that polarization is, yeah? Because as soon as you basically start measuring that photon, you will slightly disturb it, and therefore this initial polarization that I prepared is somehow washed out, and you will not be able to recover it fully. So you cannot basically make a full copy of a quantum state, and of course that is really what quantum communication, QKD especially, relies on, because you can then send those individual photons which are prepared in a certain quantum state, and nobody can make a copy and actually get key material or information in that way. And I spoke already about entanglement, which is also quite important. So, quantum computing, I think we have to mention that, because I think it does impact quantum communication quite a lot, or that's maybe one of the reasons why we're doing quantum communication. So already said, in quantum computing you have this strong parallelization, because you can basically bring those qubits into a superposition, and you can think of in a way that you can basically do then a calculation on a 0 and 1 at the same time, yeah? And that really gives you a lot of speed up for certain algorithms. And yeah, there's lots of application areas. That's why a lot of money goes into quantum computing as well. So, for example, optimization problems, for logistics, for finance, forecasting. You could also use it really as a kind of more like an analog computer, which basically simulates quantum systems in real time. So that's important, for example, if you want to improve chemical reactions or biological reactions, new drug developments, because those, to simulate really those molecules, those quantum mechanical interactions, it's really not feasible on classical computers, because the memory you would need increases exponentially with the number of molecules or atoms. So for this, you would basically need to go back to a quantum system to actually simulate another quantum system. So I think this is also a very important application. And there's also this prime factorization, which I'll come to a bit later. And this one is really one of the areas that is important to us, because this can be used to crack the currently used asymmetric cryptography. And if you've seen at the bottom, a lot of companies also in Europe are basically working, developing quantum computers. Again, progress has been really tremendous over the last decade, I would say. And yeah, a lot of money is poured into it, and I think we really will see in maybe 10, 15 years really useful quantum computers. At the moment, they've basically shown for very specialized algorithms some kind of quantum advantage, but of course they're not yet powerful enough to do the real solve the real interesting problems. So let's come quickly on this asymmetric encryption issue. So our public key cryptography relies on computationally hard problems. So what does that mean? If you basically want to send data from a sender to a recipient, you basically have to encrypt it with some kind of key. And at the moment that's done, or if you use public key cryptography, you basically have a public key, which is made out of the product of two very large prime numbers. And with this public key, somebody can encrypt the data, send it to somebody, and the other person has the private key, which is basically those individual prime numbers, and can then decrypt it. And this works as long as, since the public key everybody knows, you would think, okay, somebody could just listen in, but it doesn't work, because you really need to know those individual prime numbers. And if I give you this large n, which is basically the the product of the two prime numbers, is very, very hard for a classical computer to decompose this number again into P and Q. And that's really what the security relies on, that this is really a computational hard problem. So as long as you cannot do that, this procedure is actually secure. However, Peter Shor in 1994 developed an algorithm on a quantum computing algorithm that basically shows an exponential speed up exactly for this problem, for this prime factorization. And what does that mean? So in the classical case, if you have now time, and the number is the number of your prime number, of your number that you want to decompose into primes, and the time or the effort for a quantum computer or the number of calculations you have to do increases exponentially. That means, for example, every time I just double the number of digits, which is not too hard, so I can go from 510 to 1024 or to 2048. Every time you basically have then a factor of 10 in your time that it takes to basically solve that number. And at the beginning, you could maybe keep up with it, but you clearly see that if you make the number larger and larger, the time it would take or the effort it would take, you cannot catch up with it because it really grows exponentially. This is really for classical computation of computers using a classical algorithm. Now, if you do it the same thing on a quantum computer using Shor's algorithm, you can show that this is actually not the case anymore, and the effort just increases logarithmically. That means even if I double the number, I have a slight overhead I have to do, but not much more anymore. I don't have to basically double my number, my time or my effort or my quantum computer memory anymore. So that means that with a quantum computer, you can really, really quickly catch up, and you could, in theory, break the asymmetric cryptography. And this is really the problem that we are facing, and this is why we are basically working on QKD, which is basically offers a solution to that problem. Big question, though, I think in the room, and maybe not only in our room, is really, what does it really take now to break an RSA 2048 bit, actually? And it varies which computing platform, quantum computing platform you use. It depends on the number of qubits, errors, and so forth. But this is quite a recent paper, a few years old, and they basically estimated that you would need about 20,000 logical qubits, which means you have about 1,000 more physical qubits, because they have basically errors and you have to kind of protect them from the environment, shield them, do error correction. And they assume you have about 0.1% error probability. But if you have a quantum computer with those properties, then it would basically take about 8 hours to basically break it, which is not a lot of time. So question is, how far are the current efforts in quantum computing to those numbers? So just keep in mind about 10, 20 million and 0.1% error probability, because this is a very nice, I think, graphic showing you the progress of quantum computing in the last 20 years even. So it really started with, and this is the number of, on the y-axis is the number of qubits in the quantum computer. So it started off at low number, 2, 5, 7 qubits, and from different manufacturers, so again, different physical platforms. But you can really see quite a nice trend going up, and we are currently, so the current record is from IBM, which has basically released a quantum computer which is just above 1,000 qubits. And that prediction basically goes on. So this we had nearly a factor of 100 to 1,000 in 20 years. If we keep that for another 20 years, we basically get very close to those 20 millions that you need for breaking the RS code. And in addition, you can also decrease your error rate, because if you can decrease your error rate, you basically need much, much less physical qubits to correct and isolate your logical qubits. And this is another graph. So this is from Google, actually. So the way they want to go, so is the red arrow. So they really try not so much to go into the number of qubits, but they really want at the beginning to reduce the error. So here it's basically the error on the y-axis and your number of qubits on the x-axis. So but with the IBM computer at the moment, so we have about 1% here, which is the red dot up there, and break RSA from the numbers that I shown you before, we would basically need to be in this green area here, which means factor of 10 in error correction and a factor of 1,000 to 10,000 still in the number of qubits. So it's still a way to go, but again, based on the progress that happened in the last 10, 20 years, I think it's not unexpected anymore that in maybe 10, 15 years something will happen and that we can really go into this area of useful error-corrected quantum computing, which really then poses a threat to our security. So it's really time to act now. And why is that? Because you say, okay, my quantum computer will still be anyway away 10, 15 years, maybe 20 years, so why do I need to basically do something now? And there's the famous Moscas theory coming into play, and it depends really on the lifetime of your secret, yeah? So how long do you want actually your secret to be secure, to be safe? And it really depends then on the use case. How important is the data? Is it just basically used once, and then if somebody knows it afterwards, for example, for a bank transaction, it doesn't matter anymore, then this lifetime might be very short. If you think, okay, maybe it's insurance data, governmental data, military data, or medical data, which has to be secured for maybe 10, 20, 30 years, or for the lifetime of a human being, then I think it becomes really an issue, because that lifetime is surely greater than, or even now, than the expected development time for a quantum computer. So we really expect that in the lifetime of a human, the quantum computer will be here. You also have to add, of course, migration time, because you cannot switch your cybersecurity applications and network from one day to the other. So you basically need to prepare for it. You've seen that already now with the deployments in the EuroQCI. Countries, things do take a time to basically install it, test it out, etc. So basically, if you have to basically add those two together, the lifetime of your secret plus the migration time, and if that is longer than the development time of a quantum computer, which we say maybe 10, 15, maybe 20 years, then you have to basically do something now, yeah? So, and this is really why there's this main driver now for the EuroQCI on one side, but also from post-quantum cryptography. Because don't take it only for the quantum physicists, which of course have some self-interest of promoting QKD, but there's also the classical cryptographer scene, which is very, very worried about quantum computers as well, yeah, about the possible attacks of the quantum computer. And this is why they started already now, nearly 10 years ago already, to really think about it, and they really said, okay, we need new algorithms, new classical algorithms, which are safe against quantum computer. And they basically launched this post-quantum cryptography standardization program. I think some of them have now been standardized, but maybe Sebastian knows more about that. He's our expert on post-quantum, so please speak to him in the break. But I just want to basically, again, give the view from a not quantum physicist community. And again, they basically have this store now, decrypt later issue, which is basically this yellow part, that, okay, even if RSA and is broken later, your data now is already under threat, because somebody can basically simply store all the data which you send around now and decrypt once the quantum computer is available. So again, there it really plays into how long do you want to keep your secret, your data secure. And what they estimate in this paper, and that's from 2022, so quite recent, is this is maybe about 15 years' time. So this ties in about what we've seen with the development of quantum computing. So again, meaning that any kind of data that you want to secure or have secure for longer than 15 years or even 10 years, given migration times, you really have to think now. You really have to basically start putting a system, a new quantum secured architecture applications into practice. Good, so let's finally come to quantum communication. I've been talking about a lot about other things. So this is now really, okay, what we would like to do in EuroQCI in quantum key distribution. So in quantum communication, it's a bit wider than just quantum key distribution, as we heard from Fabiana. So what you do here, you really exchange classical and or quantum information between two distant parties. The information carrier are again qubits, so quantum mechanical systems, and they are primarily photons because they are very good at traveling, nearly at the speed of light in most media, and are therefore very well suited for bridging large distances and for communication. And what quantum mechanics now guarantees with this non-cloning theorem, also with Heisenberg's uncertainty relation, is that the exchange of information is absolutely secure, and it's secure against classical and quantum attacks. Yeah? So this, I think, is also important. So even if somebody then develops a full error-corrected quantum computer, let's say in 15 years' time, QKD is still safe, because basically it relies on the laws of nature, and you can basically show that whatever quantum computational power an adversary has, they still cannot basically crack a key which is produced by quantum key distribution. And applications area broadly for quantum communication is, of course, the main one is QKD, quantum key distribution. What we are doing here now, so this is really the distribution of symmetric keys. So you basically, at Alice and Bob, you have the same key. Before, in the slide with asymmetric cryptography, the two keys were not the same, actually, because one was basically this public key, was this product of the prime numbers, and the private key were actually prime numbers. Here it's different. You have really symmetric keys, so Alice and Bob have the identical key, and this key is really guaranteed, if you do a right implementation of the protocol, to be secure, and nobody else knows about that key. And then you can basically use some classical encryption algorithm using those keys to encrypt your message, transmit it encrypted. Nobody can read it because it's just garbled mess, and then you decrypt it at the end. Another part is QNG, so quantum random number generation. Again, you can basically use the laws of quantum mechanics to give you this kind of ultimate randomness, because inherently in the theory itself, if you have this collapse of the wave function, it should be completely independent of any outside influence. And again, nobody should be able to basically know when it collapsed or which way it collapsed. So that gives you a very good randomness, which you might need also for either some classical algorithms or other application. You can do a bit more as well. You can do some multi-parted computation, again, securing information exchange. In this case, it's more collaboratively, but between entities that don't really trust each other. Yeah? In QKD, you basically have Alice and Bob really fully trusting each other. You can do other protocols where basically people don't trust each other, but they still want to work together. They still want to kind of collaboratively work together on their piece of information, but they don't want that the other party knows this piece of information. So again, here you can use quantum algorithms to enhance the security. And then finally, if we come towards the quantum internet, which basically relies on the exchange of entanglement, long-distance entanglement using quantum repeaters, quantum teleportation, the idea here is really to link up distance quantum computing centers and then have some kind of larger distributed quantum communication going on, or using quantum sensors that are connected using entanglement. So this will be the final stages of a full quantum communication network, but as Fabiana said, is also part of EuroQCI. It's not the part we are talking now, it's not going to be the near term, but for the mid-long term, we also have to think that we would like to basically get those technologies also out. And especially the quantum repeater would be tremendous helpful for QKD, because in QKD we still have at the moment the issue that if you use an optical fiber, you have exponential loss of the photons in this fiber. That means you have a distance limitation of a few hundred kilometers, after which you have to basically either stop the transmission and hopefully your recipient sits there. If not, you basically have to then re-encode it into another QKD link, but then you're kind of vulnerable there that somebody attacks your key because it's available in a classical form. So you have to basically put a trusted node, a protective environment around it. If you would have a fully fledged quantum repeater, then you could really exchange quantum information more or less indefinitely, at least around the world, in optical fibers, and that would mean that in between you don't need trusted nodes anymore, and even if somebody tries to listen in, again, the key would be fully protected by quantum mechanics. So I think it's quite important also for us, for QKD, that developments are going forward. Okay, some advantages. I think I've already mentioned some. So it's really this forward secrecy also, that you know that somebody which is now encrypted using QKD keys will basically stay secure even in the future, because even if somebody tried to basically lock this data, even with a powerful quantum computer, in 15, 20 years' time, they still cannot break it. And I said it might be for certain data very important to have this very long-time security. It's ITS secure, so it's really information theoretical secure, so you can really prove it mathematically that is secure against all possible attacks. You could then, for example, combine it with a one-time pad, which is also ITS secure, to have basically a full secure encryption and decryption of your data. And again, this might be very important for some very highly confidential data in the government or military context. Also maybe for critical infrastructure that nobody wants that maybe their power plants or electricity grid is taken over. So for this we can have really very high security offered, and also dynamic keys, so fast renewal of keys is possible. So again, if you use AES, which is basically an encryption or a very widely used encryption protocol, you basically just need a very small key to encode or encrypt a lot of data. But again, you should basically keep changing this key from time to time, because otherwise there might be it might become unsecure. And for example, here there's one estimate or one recommendation for every 60 or so gigabyte of data, you should basically use a new AES key, and the AES keys are normally 256 bits long. So this is something you can then easily do with QKD. Also crypto agility, so you can compare it with post-quantum keys. You can basically switch between the two. So it gives you, a lot. So for governments, this I think is the point we want to talk here. I think you've seen this. I just showed a slide because you've seen it from Fabiana. It's really the EuroQCI, really the first use cases. The first users should be really those governmental bodies using QKD in Europe, connecting them between each other, connecting them to the European Commission in Brussels. And we have basically those two segments to do that. One is the fiber-based one, which is maybe easier to roll out. We're already doing that in many, many countries, also in Greece. Has, of course, the issue with this distance limitation. So you have to basically put those special secured trusted nodes in place. And the other way is going via the satellite, where you don't have the distance limitations, but of course you are limited at first of all that is a satellite in orbit, that you have a direct line of sight, that there's basically not too much light around it, which could basically interfere with your transmission. And also the ground station needs to be located somewhere where, again, you basically use the key. Otherwise, you have the same problem with the terrestrial network, that you again have to put long fibers from your optical ground station to your actual users. So quickly about the EuroQCI timeline, and this is very tentative, so it's not approved by the Commission either, I must say, if Fabian is listening. This is just what I think will happen. So at the moment, there have been some studies going on in early 2020s. Now we're really in this first proof of concept, first deployment phase with our DEP projects, where basically each country is trying to build up a first QKD network. That will be followed then now by two initiatives. So the first one should be focusing on cross-border and deployment of ground stations. So this should be the CEF2 call. And the other one will be a second round of TEP projects, where again those initial networks in the member states will be enlarged. New technologies will come in, and then with the cross borders, hopefully we have a first kind of links in Europe that are going between many countries. And about the same time, so we expect, I think, end of 25 or somewhere in 26, the launch of the first European QKD satellite, so that's the Eagle 1 mission. Again, for this, hopefully the ground stations are in place then, so that validation can start pretty immediately. At the moment, Eagle 1 is not it's not foreseen to really use that already for communication or for exchange of confidential data, but it's really, again, just a kind of a test bed to basically try out the technology, see how the ground stations work, how they're interconnected with the terrestrial network, and how it basically works to basically share this one satellite between the different member states and see who can be connected. And then we have the full operation, hopefully with devices that are fully certified, I think, by the end of this decade. And this should also then go together with the Saga mission. So that's a second initiative by the European Space Agency to launch then some satellites, maybe even based on entanglement, to have a real operative, an operative aspect, and meaning that the keys then exchanged by these satellites can be used for encryption of confidential data and exchange between the member states. So this is roughly the time frame, so still some things to do. I will go through this. So speaking about technology, what's available now, so I've shown you very early on those pictures of the first experiments. I mean, by now we really have an advanced QKD ecosystem in Europe, so I'm really grateful that some of you really made the effort to basically say, okay, I want to have a company now here, and I really want to support this development using maybe even my components, or I provide software for it. So we have several component suppliers. We have quite a lot of QKD system manufacturers here now, which have a very high TRL. As I said, you can really get those boxes now. You put them in, and basically they run out of the box, more or less. Apologies if I don't have all the companies on it. So I think there was already some that I missed. Also, key management, so this is a higher layer. I have not gone much into networks, but I think there might be talks coming on later on. So those are companies who are basically providing, on top of the physical layer, the key management layer. So if you have a very large network, you don't need necessarily a QKD link between any two nodes in your network. So you can basically just make sure that each node is at least connected by one QKD system, and then you basically exchange pairwise keys. And with the key management on top, you can then basically combine those keys to make an any-to-any key between any points in the network. And that's, some companies have specialized there. And also then what's important is also how do we use this key. Yeah? So this is what is really the end user of the key, or what's the end, or the system that's the end user of the key. And in a lot of cases is some kind of hardware encryption module where basically the key is read in, and then that key is used in a classical encryption algorithm. It doesn't necessarily need to be a hardware encryptor. You could, if you especially think, okay, you want to combine it with post-quantum keys, you might have another layer just before which basically combines those keys from the different domains and then feeds it forward to some kind of encryption device. Use cases, so I'll just go through that very briefly because I think we will hear much more. So this was one use case a couple of years ago which was demonstrated in the city of Graz in Austria. So that was a 4-node network, 4 links, and it was used to basically secure medical data and store them safely and then retrieve it again between different hospitals. What's important, I think it's maybe the kind of stakeholders that are involved in such a, again, it's a proof of concept demonstration, but you have basically the end users and the service provider, so somebody has to provide your fiber. You basically want an end user who really does something with the key or has the data that needs to be encrypted. The infrastructure provider that sends data centers here, and the device manufacturers, both for the QKD and also for the encryption devices. Then on the deployments, again, that's the left one is from the OpenQKD project. So this is currently the largest network, QKD network that we have in Europe, which is in Madrid. So they had 10 nodes there, 13 or more, 13 links, but many more devices because they could actually switch between different devices as well, and several link encryptors. And I think important point here was really that it was incorporated into the network of Telefonica. So basically, using existing telecommunication infrastructure, existing production networks to basically just put in QKD on top of it, because it's very expensive otherwise if you have to basically build up a whole new fiber infrastructure just for QKD. So the idea is really, if possible, use existing infrastructure in existing networks, and of course you have to then see how you can achieve that with the providers. And the other one, I think that's also, I think, very nice and relevant to EuroQCI is those first cross-border experiments that was between Croatia, Slovenia, and Italy. So they were basically linking 3 cities together and used that key then to secure a VPN connection over which they had a encrypted video running. So, last slides before I finish. I think a lot has happened. I think we are in a really good way. We've done a lot. However, to have a really fully operational EuroQCI that you can really use for confidential data encryption and transfer, there's a few things that still needs to be done. So first is a kind of SDN functionality, so software-defined network functionality, which basically gives you much more freedom in the network to basically route keys in different directions, maybe change wavelength of the quantum key, especially if they are together on the same fiber with classical traffic. We have to think about this key forwarding in a bit, or there are several options available, so we have to decide on one, or make at least sure that there are kind of interconnectable. This is the key forwarding is really this kind of hopping of the keys if you have a long distance. And as I said, you basically have to break the QKD link. You have to have the key classically, and then you have to re-encrypt it, and you do that for a couple of hops in order to bridge maybe 1,000 kilometers. And there are basically different approaches of how you can achieve that. Then I think also this domain exchange, because it's very likely that the EuroQCI will not be just a single domain, which is basically controlled by a single controller, but probably each country will have their kind of own domain, and they want to be, of course, in control for some obvious reasons. But then again, if you have 2 domains, they can maybe talk together. But if you have 3 domains and you have to tunnel through one, then it becomes again tricky. And then you have maybe the satellite as an additional domain. So things have to be talked out, resolved. It's not a technological issue, I think, but it's more one on regulations. Authentication, I think this is one part that will I don't know if somebody will address it today, but in order to basically bring in new systems in your network, you have to somehow authenticate it, yeah? You have to say, okay, this is now a legitimate device in my network, and this can be either done by really going to the device, upload a first key, which of course in a larger network is not so useful anymore, or not very practical, or one could maybe use some post-quantum technologies or algorithms in order to do that. And hybridization, I think this is very interesting as well. So this is kind of a combination then of QKD and post-quantum to get the best of both worlds out. So you kind of feed in both keys, and then you kind of make a kind of key derivation to end up with a key which basically has the additional security of both versions, of both algorithms. And finally, certification. I will talk of that briefly in my next talk, which I think is also very important. Good. So with this, I think I'm nearly closing. So as for visions, so I would like to show you the slides I showed 20 years ago in Crete, which was this one, which was really about basically distributing entanglement via satellites or having a ground link. And it sounded like a vision then, but it really became a reality, a bit more than 10 years later. This was the MICU satellite launched by the Chinese. So again, if there's a will, one can really, the technology is there, yeah? If one has to really say, okay, we want to do that, we want to achieve that, if we work together, I think we can really realize it. And even before the Eagle 1 satellite, the first European QKD satellite, the Cube, was launched a couple of weeks ago. That's, I think, a German mission, though. I'm not sure if we have access with our ground station to that, but just to let you know that we're at least in Europe catching up a bit with other nations. So this is maybe then my vision for in the next 10 years, and I'm pretty confident that we will achieve that. And I hope, Elias, you will organize in 10 years another conference to see if I was right. I think we will really, by 2035, I think we will have this, and hopefully before, but I think this is a conservative estimate, to have really this fully operational pan-European QKD network. Because again, the technology is there. I think we just have to sort out some of the regulatory parts. We have to make sure devices are certified, but I think otherwise there's really nothing standing in the way of realizing something like this. And maybe, as Fabiana was saying, we even have some more general quantum communication networks, maybe having some small quantum repeaters or even quantum computers that are already interconnected by that time. And with this, I would like to thank you for listening.